To first understand how to find habitable exoplanets, we need to understand what they are. Habitable exoplanets are defined as extrasolar planets with the right size and orbit to support surface liquid water. Extrasolar planets are a relatively new discovery. Evidence was only found during the mid-1990s, and therefore no analysis could be done until now.
Focusing on the dynamics of stars and their potential for habitable planets, we can take a look at the possibility of multiple planets within the habitable zone, as well as the ratio of planets to the star's mass. This figure shows the survival of planets within the habitable zone relative to the mass of the star. The dynamical limitation to the packing of habitable zone terrestrial planets is about 5 planets for most spectral types, and about 6 planets for stellar masses greater than 0.7. Low-mass stars highly favor 5 planets over 7, but high-mass stars greater than 1 solar mass can take on 5 to 7 planets without becoming unstable. A particular example that is shown to be promising in finding extraterrestrial planets can be seen within the star system Beta CVN, a G0 star located in the Canis Venatici constellation. Its lack of high-mass planets, such as gas giants like Jupiter, and its sun-like parameters increase the likelihood of survival within its habitable zone. Another system, TRAPPIST-1, has been found to have multiple terrestrial planets in the HZ, making us question whether such dynamical packing in the habitable zone is normal or rare.
Next, we can look into the work done by Andrea Buccino into the possibilities of habitable planets orbiting Class M stars. Specifically, the team looked at the levels of ultraviolet radiation coming from the stars. Each planet looked at existed in its respective solar system's liquid water habitable zone. UV radiation has been understood in previous studies to be necessary in forming many biochemical compounds, in which it acts as an energy source. However, too much UV radiation has been shown to inhibit various forms of life, as it can deconstruct DNA and block photosynthesis. The purpose of Buccino's research was to see if exoplanets that existed in the liquid water habitable zones of Class M stars would also receive the right amount of UV light to stimulate biochemical growth and not too much that it inhibited it. By taking data of the variance and intensity of solar flares, the scientists were able to observe the amount of radiation each planet received. The findings disappointingly concluded that Class M stars do not produce enough ultraviolet radiation to stimulate the growth of these compounds at the same range of orbit that liquid water can exist. This is important because 75% of main sequence stars are Class M or similar in size, and understanding that they would not be able to support life helps narrow the search for Earth-like planets.
The research done by Pinter, Paranova, Lux, and Pathak wanted to answer the question, is there any particular spectral class in which habitable exoplanets are more probable, with the goal of helping to determine more exoplanets with ease? Currently, there are 3 main habitability metric systems used to determine a habitable exoplanet, which are the Earth Similarity Index, the Planetary Habitability Index, and the Standard Primary Habitability. Using these equations, the researchers were able to calculate the following tables using data from previous literature by Morris in 2010 with outputs on occurrence of exoplanets in habitable zones. The data they computed is as follows. The biggest trend found from these tables is that the greatest occurrence of exoplanets happens in the main sequence G stars. To discover more habitable exoplanets, this class of stars serves as the best case to detect them. The hope of this finding is that it is useful to detect more habitable exoplanets by focusing on the main sequence G stars.
Finally, a study done in 2013 by Ravi Kumar Kopurapu used an updated radiative convective cloud-free climate model based on the 1993 Casting et al. Model to obtain new estimates for habitable zone widths around F, G, K, and M class stars. These were modeled around the habitable zone boundaries of stars with stellar effective temperatures of between 2600 and 7200 Kelvin. The inner edge of the habitable zone was determined by water loss, while the outer edge was determined by the greenhouse limit using the updated casting model. This new model indicates that near the inner edge of the habitable zone, there's no clear distinction between runaway greenhouse and water loss limits for stars with effective temperatures greater than 5,000 Kelvin, which can impact current ongoing planet searches around K and M class stars. In addition, the study found that the effective stellar flux is more accurate than equilibrium temperature to determine habitability zones. This removes the dependence on planetary albedo, which varies depending on the host star's spectral type.